Hello to you all. Myself, Dr. Tilak Mukherjee. I am here to present the topic on electromagnetic waves, means the EM waves, and the physics behind the formation of the waves, and what are the governing laws that defines the waves. The content that we will have in this presentation is what are the fields, what are the overview of the fields, means what is meant by the electrostatic fields or the magnetostatic fields. What about the concept of the time varying fields? What are the important Maxwell's equations that are related to the time varying fields? The medium and the boundary conditions that we have at the interface, the important wave parameters of interest, EM waves, and the various modes that we come across, and the other different EM wave phenomena. Now, the first of all, I would like to state that electrostatics, when we talk about the term, that means the electric charge is at rest, that is not in motion. That can be the line charge distribution, it can be a surface charge distribution, it can be a volume charge distribution, or it can be a simply point charge also. So all these static charges form the electrostatic field. But when you have a DC current or a constant or a steady current source, that time you have the magnetostatic field or the magnetostatics. Now, if there is a variation in the current, for example, take the AC current, then what happens? Then there is a changing electric field. So this changing electric field gives rise to changing magnetic field also. So these time varying electric and magnetic fields are interrelated. Means if there is a changing electric field, there is also a changing magnetic field. On the other hand, if there is a changing magnetic field, there is also a changing electric field. So they are always in pairs. So we call them changing or the time varying electromagnetic fields. They actually are the main cause for the formation of EM waves, or we most commonly call them as the electromagnetic waves. Now, what is a wave basically? It is a carrier of energy and information that is represented in terms of both time and space coordinates. Means because it's a variation, so at time t1, what is the location of the wave? At time t2, what is the location of the wave? So this has to be expressed in terms of certain coordinate systems. So for that reason, we come across the different kinds of coordinate systems. Mainly the important coordinate systems are the Cartesian or the rectangular coordinate system, the cylindrical coordinate system, and we have the spherical or the polar coordinate system. Now this is the diagram of the various kinds of orthogonal coordinate system that we have. X, Y, Z, they represent mainly the rectangular coordinate system. Rho, phi, Z, they represent mainly the cylindrical coordinate systems. On the other hand, in the spherical coordinate system, we have r, theta, phi. This is mainly used for the analysis of antenna and all to study the radiation pattern and all. Now coming to the next slide, what we see, a brief overview of the vector calculus that we often come across. Mainly we have two important operators, one is the del operator and one is the Laplacian operator. And some important operations we have, take for example the gradient operation, the divergence operation and the curl operation. The gradient operation is always on a scalar quantity, the divergence operation is basically on a vector quantity, and the curl operation is on a vector quantity. They all have their individual significance. Gradient denotes the rate of change of space of a certain quantity. The divergence denotes the difference between inflow and outflow at a particular point. The curl operation denotes the means how that particular vector quantity will rotate, or what is the degree of angular rotation that is represented by the operation curl. Then we come to the Stokes and divergence theorem. They relate mainly the line integral into the surface integral, and the divergence theorem mainly is giving the relation between the surface integral and the volume integral. So they form mainly the pillars of the vector calculus part. Now coming for the static fields, mainly the static electric fields and the static magnetic fields. These are the four Maxwell's equations. One is coming from the Gauss law, the first one, that is del dot D equal to rho V, del cross equal to 0, that means the static electric field is conservative in nature. Del cross H equal to J bar, this is the conduction current density. This is coming from the Ampere circuital law. And one is coming like del dot B equal to 0. That means we cannot have separate magnetic north pole and south pole. So non-existence of magnetic monopoles. This is basically denoted by del dot B equal to 0. So they are the mainly these four Maxwell's equations are for the static fields. Now here comes the concept of EM waves. What about the time varying fields then? For the time varying fields, we will see that according to the continuity equation, we see that it has to follow the law principle of charge conservation. So if this is the case, I out is equal to minus dq in by dt. And this is meant by the full continuity equation. By this simple derivation we see, we convert this into the current density form, and similarly we also convert this is the surface integral, this is the volume integral. We apply here divergence theorem, convert the surface integral into the respective volume integral, and finally we equate the right hand side and the left hand side. We get this equation, mathematical expression, del dot g equal to minus dou rho v by dou t. That means this is the continuity equation. Now coming to this extension, what we see, suppose we have considered a capacitor, so simply a parallel plate capacitor. Now when we connect the capacitor to a AC source, then what will happen? At one plate positive charges are formed in one cycle, and in the other plate negative charges are formed. Again when the cycle changes, there is a displacement of charges. In the next cycle, here again negative charge, here again positive charges are formed. This goes on continuously. So this changing electric flux or the changing electric charges gives rise to a time varying field. And this is the main reason for the formation of displacement current. A very important concept in EM waves. This is known as the displacement current. So displacement current density is denoted by the quantity dou d bar by dou t. Dou d bar by dou t means the main thing is this is the displacement current density. So it's time varying in nature. So what we see that displacement current is a result of time varying electric field. Of course, we have taken the example of a capacitor that is connected across an AC source. So AC source is itself, it is not a constant source. It is the time varying electric field. So due to that, we are having displacement current. And the typical example of such current is that when we consider a capacitor, when an alternating voltage source is applied to its plate. The same has been explained in the previous slide. Moving further ahead, then what are the general, moving further ahead, we come across one more important law, that is the Faraday's law of electromagnetic induction. What we see, if there is a coil where you have a certain number of turns, and what happens if the magnetic flux changes, then what happens, this dou phi by dou t, this also changes, where n is the number of turns, then an EMF is induced. This EMF, the direction of this EMF is opposite to the cause that is producing it. This is according to the Lenge's law. So the target is that if somehow you are able to produce a changing magnetic flux, this dou phi by dou t, this is changing, you are able to produce a EMF. Okay, so this is meant by the Faraday's law. Now, based on these two things, what we see that the equations that were valid for static fields, we see if we consider time varying field, there is a certain difference. Coming to the first one, that is the Gauss law, del dot d equal to rho v. This is the same. Whether you consider static fields or time varying fields, this remains the same. This is the differential form of the equation. This is the integral form of the equation. The non-existence of magnetic monopoles. This equation also remains the same. Del dot v bar equal to 0. These two equations remain the same. But coming to the third equation, del cross E bar, that is equal to minus dou B bar by dou T. This is actually coming from the Faraday's law of electromagnetic induction. That means if there is a change in B bar, that means the magnetic field is changing. You are having a changing electric field. Coming to the fourth equation, del cross H equal to J plus dou d bar by dou t. This is also further extension or a more modification of the Ampere's circuital law. Now, if you consider static fields, that means you are having no term of dou by dou t. Static fields means the differentiation is equal to z e dou. So this term will be 0. This term will be 0. In that case, your equations are becoming same like the you consider for the static field. That means this term del cross E bar will be equal to 0 and del cross H bar will be only equal to J bar. So these two are the changes that occur when you consider time varying fields. The introduction of this term minus dou V bar by dou t and the introduction of this term dou d bar by dou t, that is the displacement current density. This is the simply a diagram or just a schematic diagram of how the EM wave propagates. This is the x-axis, this is the y-axis, this is the z-axis. Along the x-axis, we have assumed the direction of propagation. So along the other two axes, the perpendicular axis, you are having the electric field and you are having the magnetic field. So this means that is basically transverse in nature. Means the fields and the direction of propagation, they all are mutually perpendicular. So this is one important property we can say of a EM wave. Medium and the boundary conditions. What we have? We mainly see there are different kinds of medium, but the nature is for the sake of our simplicity or the assumption, we consider sometimes the medium to be linear. We sometimes consider the medium to be homogeneous. Sometimes we may consider the medium to be isotropic. So all these terms are how they are varying with respect to D, with respect to E, whether the medium properties are same or not. That time that will be a homogeneous medium and so on. The classification of the medium is basically depending on three things. One medium is simply the air or the free space. One medium is a dielectric medium, and one is a conducting medium or a good conducting medium. Where you have the sigma value very low or insignificant, that is the dielectric. Where you have the sigma value very high, that we call as the conducting medium. If the sigma is totally absent, that is the 0. So this term is very important. Free space, one is the dielectric, one is the conductor. Coming ahead, what are the boundary conditions? Suppose you consider this is one separate medium 1, this is one separate medium 2. At this medium 1 and medium 2, this is the border, this is the edge. So that is known as the interface. What are the conditions that will govern the electric field as well as the magnetic field regarding the tangential component of the field or regarding the normal component of the field? That is mainly meant by the boundary conditions. So we have in electromagnetic 4 important kinds of boundary conditions, like what are the E tangential 1 equal to E tangential 2, or the normal component of the T, that means the electric flux density is equal to, they are the same. H tan 1 is not equal to H tan 2, that is equal to some term J of H, that is the surface current density, but Bn1 equal to Bn2. So what about the normal component is along this? What about the tangential component along this axis? So we mainly call them what are the various conditions that will govern them? That is meant by the boundary condition. Coming to the next part, important wave parameters of interest. Now, whenever we are analyzing a wave or when you want to study about the propagation characteristics of the wave, we mainly convert the dou by dou t term, we convert that into the phasor form because it is easy for us to represent, because that is basically sinusoidal variation term. So single derivative will give g of omega, and you have more higher order derivatives of dou by dou t, that is means the raised to the power of n. So in that way, we will define the wave parameters. And the important propagation parameters that we have are mainly basically the wave velocity, that is the v, very important. What is the phase shift constant? That is the beta. What is the wavelength of the wave? That is expressed in terms of lambda, that is 2 pi by beta. what is the attenuation constant alpha, what is the intrinsic impedance, the intrinsic impedance of a certain medium that is given by the term eta. Propagation constant, this is a complex term, this is equal to the real part alpha plus j beta, where beta is the imaginary part. So propagation constant, attenuation constant, phase shift constant, wavelength, intrinsic impedance, they are very important wave parameters. Apart from them, we have some median constants like what is the permittivity, that is denoted by epsilon, or the permeability, and what is the medium conductivity. Now, if you consider free space, this medium constant epsilon, that is equal to epsilon naught. Similarly, the permeability mu, that is equal to mu naught. Okay, so what is the concept of the wave? What are the important equations that govern the formation of the waves? What are the important wave parameters? These have been focused. Next, coming to different types of medium, as already explained, we mainly do the certain approximation. If this term, the sigma, is much less than omega epsilon, that particular medium is termed as a dielectric. If this sigma is much greater than omega epsilon, that medium is known as a very good conductor. And if simply this term is 0, sigma equal to 0, that becomes a free space medium. So, definitely this is having a very important role in classifying a medium. So, this term sigma by omega epsilon ratio, this is known as the loss tangent or the dissipation factor. Okay, and based on this, whether this is much less than 1, that will be termed as a dielectric, much greater than 1, that will be termed as a conducting, or simply that's equal to 0, that is termed as a free space. And accordingly, we have the important wave equations. Del square E equal to mu epsilon E dot dot. E dot dot denotes the double derivative with respect to time plus mu sigma E dot, single derivative. In terms of magnetic field, the same equation, just E is replaced by H. So they always, so the wave equations, they are not actually in singular in number, they always exist in couples. So one is expressed in terms of electric field, one is expressed in terms of magnetic field. Now, what you need to do, whether according to the medium, whether that's a good conducting medium or a dielectric medium or a free space medium, just you substitute these conditions and you generalize these equations and you get the wave equations. They are also known as the Helmholtz wave equations. Uniform plane wave. Uniform plane wave means if along the direction of travel, that will have no electric component or the magnetic field component. That is known as the uniform plane wave. That is also commonly, sometimes we call them as the TEM mode. That is mainly taking place in transmission lines or in free space. But sometimes this is not true. Sometimes along the direction of travel also, any one field, either the electric field or the magnetic field is present. So those modes are known as the TE mode or the TM mode, means transverse electric and transverse magnetic. So we come across certain mode terms like what is meant by TEM mode, transverse electromagnetic. Along the direction of travel, there will be no fields. TE, TM, they will not exist in transmission line. They will mainly exist in wave guides. They are also one important part of guided communication. That is the transmission line and the wave guides. Apart from this, also the EM waves exhibit certain phenomena. Like take for example the reflection. They also obey the Snell's law of reflection. They have refraction, that is the bending effect when they move from one kind of medium to the other medium. According to the refractive index, they may bend away from the normal or bend towards the normal. Then you have the total internal reflection also. You have the diffraction, where along small apertures, the wavefronts will get diffracted. Interference effect, they can be constructive or destructive. Polarization, the wave can have different kinds of polarization also. That will depend according to the locus of the electric field's circle. They can trace a linear path, that is the linear polarization, or a circular polarization or elliptical kind of polarization. And the power density of the EM wave, that is mainly represented by the term Poynting vector. So how much power density means, what is the watt? Power density means how, means suppose a wave is basically consisting of time varying electric field and magnetic field. Now these magnetic fields and electric fields are having certain energy density associated with them. So whenever a wave is falling on a certain medium or on a certain surface, what is the power per unit area? That is represented by the Poynting vector. That is exactly what we mean by power density, where the units is simply in watts per meter square. Okay, so we come across various phenomena like what is the, means it is basically transverse in nature. How to represent, how to express the power. It can be polarized. There is polarization. There is interference. There is diffraction. There is the effect of total internal reflection. We have reflection. We have refraction. And similarly, accordingly, they will follow the Snell's law, as we have seen in physics. And this is a part of the electromagnetic spectrum which we come across. And accordingly, first of all, we have the radio waves. Then as the frequency range increase, we have the microwaves. Then we have the infrared. Then we have the ultraviolet, and finally X-ray, gamma rays. As the range of frequency increases, we from kilohertz to megahertz to gigahertz to 10 to the power to 12. So finally, this is the range of the frequency. Terahertz. This is a part of the electromagnetic spectrum. Now, the important books that I will suggest in this part is mainly the Jordan and Norman and the Sadiku book, that is the Principles of Electromagnetics or the Electromagnetic Waves by Shiv Gaonkar. And one Indian author book is also very good, that is the Jason Raju. And of course, some MOOCs or the NPTEL video lectures that we come across while dealing with such topics like what is the wave, what are the maximum equations, what are basically the different kind of media, what are the important laws that govern the electrostatics, or what are the different laws that govern the magnetostatics, whatever the concept of time varying waves, what are the wave phenomena, what are the wave important parameters. So in this presentation, we have mainly focused on these aspects. Thank you.